Hey everyone, thank you so much for joining us. I'm Justine. I'm a senior program manager at Microsoft. I work on the Cosmos-db team, and I cover a lot of cool features in the SQL API, including some of our SDKs and, of course, the query engine, which we'll be focusing on today. Chander, do you want to introduce yourself?
Absolutely. Hey everyone, I'm Chander Dhall. I'm a Microsoft MVP and an RD, and I'm also a CEO of Cazton.
Cool, great. Well, thanks for joining us. We also have with us today our wonderful moderator, Chris Hyde. Thank you so much to Chris. He'll be moderating the chat and answering all of your questions. So feel free to stay engaged and type questions in the chat as we go along. We'd love to hear from you, and Chris will help us out with those questions. So today we're here talking about how to customize an indexing policy in Azure Cosmos DB SQL API. We'll be following this Learn module. So if you want to check out the Learn module for yourself, you can go to this link or follow the QR code. We actually don't recommend that you follow along with this module while we're presenting. We really want you to stay engaged and listen to all the content, but it would be great to check out after and make sure that everything we covered today really makes sense and lands for you. We also want to mention that there's a certification for Azure Cosmos DB. So be sure to take this certification at the link or with this QR code if you're interested in measuring your ability to create solutions using Cosmos DB, covering data modeling, design, distribution, lots of great stuff here. So please take this certification if you are interested.
Oh yeah, and this certification is definitely a good one. I tell you what, anytime I go to my employees, hey, would you like to have a certification? They're like, oh no, it's so boring, it's so theoretical and things like that. And this one, Imran took that in January, and he was like, wow, this is one of the certifications where I had to think through things, and I felt like I'm using what I apply in real life. So it wasn't really that boring at all. In fact, he loved it. So I definitely highly recommend this one.
Yeah, that's great. Cool. So what are we going to be learning today?
Well, good stuff. I mean, indexing policy definitely is a very, very important key aspect of any distributed database system. So we're going to focus today on read-heavy workloads as well as write-heavy workloads, because those are definitely the two important ones. And the good news is that we have a lot of code. We don't just want you to have to see PowerPoint. We're going to go back and forth and show you a bunch of these queries and how they work, what kind of RUs they have. And we hope it's going to be interactive. So just remember, it's live and interactive. So please go to the chat, say hi, where you're from, and shoot us questions. And we're going to be taking a lot of live questions, right, Justine?
Yeah, we will. We really want to hear from you. So feel free to ask us questions and we'll answer them live on air.
Yeah, that'd be great. And also, one of the main things about Azure Cosmos DB is that it's actually schema agnostic. A lot of people use words like schema-less and things like that. Well, of course it has a schema, but it's actually schema agnostic. You can basically say something like you have a person, a document that could literally have, a given name property. And for the next record, you could literally have a first name property. And that's so cool about it, right? You can have a date and you may not have a date in the next record, but there's still a schema, but you don't have to really adhere to one. And that's pretty cool. At the same time, a lot of people are like, well, this is Microsoft's NoSQL database. And I was like, no, well, actually, there's a lot more here. We have 5 different kinds of consistency levels and things like that. But again, today we're going to focus more on querying as well as, the indexing policy behind that and, how that works and what kind of RUs you consume, both on read-heavy as well as the write-heavy workloads. So that's going to be exciting.
Yeah, I can't wait to dive in. So as we're talking about indexing, of course, it's important to understand how your index is actually being used so that we can further optimize our queries for these two patterns, either read-heavy or write-heavy. So when we think about index usage in Cosmos DB, there's actually 5 different ways that the index can be used in your queries. And we've listed them here in order from the top being the most efficient index usage to the lowest, the full scan, which actually doesn't use the index at all. So let's cover each of these different methods. First, we have an index seek. So in an index seek, the query engine is actually seeking an exact match on a value in your index. And this allows it to only read the required index values and load only those matching items from the transactional store. So this is a really efficient way to use the index. It's used for equality filters. So say, property equals value, or if you have an in clause. And there's also some RU implications for this. So it's important to point out when your charged RUs for queries, the charges come from a variety of different things, but it boils down to two buckets, essentially. The first is the RU charge that's actually from the index lookup, and the second is the RU charge for loading the documents. So for an index seek, because we only need to read the values from your index that are required, the charge is actually constant for the lookup. So it's a really small charge for this lookup, but you'll be increased linearly. You'll be charged with an increase linearly based on the number of items that are actually returned. So if Cosmos-DB needs to load a lot of documents and return back a bunch of documents, especially if they're quite big, your charges will increase based on that. Now, the next three index usage types are all kind of go together. So these are all the scans. And there's three types of scans that you can do in Cosmos-DB, and they range in efficiency. So the most efficient is the precise index scan. What this allows for is actually a binary search of your indexed values, and we only need to load the matching items that from the transactional data store that actually match whatever your filters were. So you can think of this as comparison operators, greater than, less than, or also a starts with clause. If you're using starts with in a case sensitive way. So, making sure that the letters in your string are actually the proper casing that you've passed in your query. So for this, because we have a binary search, which is very efficient, your RU charge will increase slightly based on the cardinality of the index properties. So the portion of your RU charge that comes from the index. And what this means is if you have a really high cardinality property, so think the ID property, the cardinality is massive, right? That's one ID to one document. That's the highest cardinality you can have. Your RU charge might increase more than if you were querying on a property that has a lower cardinality. So say US state, there's only 50 states, right? So for the precise index scan, you'll also get an increase in charges based on the number of results that are actually returned. The next one is the expanded index scan. So this is really similar to the precise index scan, but instead of using that more efficient binary search, we're going to get a slightly less optimized search for your indexed values, but this is still a relatively efficient scan. And the items that we actually load back from the transactional data store are still only the items that actually match what your query filter was. So similar to the precise index scan, for your RU implication, you will see slight RU charges based on the cardinality of indexed properties and also based on the number of items that are returned.
So the cardinality happens to be a very key aspect of everything because at the end of the day, it's really how much data you have and what kind of cardinality you have. For those people may not necessarily know cardinality because a lot of times I get confused with terms like that. Think of that as just the number of items in a set. So if the numbers of items in a set happen to be 200 versus 2000, 2000 is going to have a higher cardinality, as simple as that. By the way, there's a great question from Dara Ethiopian. If I could pronounce your name correctly, apologize if I didn't. But the question is, would you like to discuss about performance tuning? The good news is that once we cover these slides, Justine's going to show you a lot of different queries we're going to do based on these precise scans that we're talking about here. And we're also going to explain to you why some of them are taking more RUs and what you can do to actually change that. And if you do, what are the pros and cons? So we're definitely going to cover that aspect for sure. Justine, so what do you think about the full index scan? Do you want to talk about that?
Yeah, so the full index scan is the last in our set of index scans, and it's the least efficient. So in this case, you're reading a distinct set of index values, and you're only matching the items from the transactional data store that are actually matched. So in this case, we have to read the most number of values from the index. So this means that instead of the RU charge increasing slightly based on cardinality, it's actually going to increase linearly based on cardinality. So if you have a property with a lot of values, your increase for your RU charge will be higher. Now, in this one, you're also only charged based on the number of items that are actually in the results for that second bucket, the document load time. Lastly, we also have the full scan. So it's important to note that this type of query actually doesn't use the index at all. So if you're using a full scan, you need to load all items in their entirety from the transactional data store. But don't worry, this full scan is not very common. Obviously, the goal here is that you can write your queries such that they're able to utilize the index. One way that you could see a full scan is if you're using some system functions in combination with aggregations. So we'll actually show you an example in a little bit that uses the full scan, and we'll show examples for all of these index usage types to really drive this point home and the RU differences between them. But before we get to that, I want to talk a little bit more about the index usage. And when we talk about the index, like, what does that actually mean? So let's take this example container with 3 simple documents. We have 3 documents here with an ID, a name, and a price. So we can actually represent these documents as a tree. This is going to form the basis of our index. So let's say for document ID 1, we can create a tree with 1 at the root. We have 2 children for the 2 properties. We have a price node and a name node, and each of those has a child for the value. So in this case, price is 775, and the name is Touring 1000 Blue. Okay, so that's great. We can create a tree out of 1 document, but what does that mean for our index? Cosmos-db actually uses something called an inverted index. So what this does is it creates a tree out of all of the documents in your container, and it will be able to map them to certain properties. So you can see here at the root, we have all of the IDs for our container. Remember, we only have 3 items. We have 1, 2, and 3. And all of those 3 items have the same 2 properties. So we have a price node and a name node, and each of those have their distinct values. So as you can see, 675, which was our price for document 1, has a little 1 next to it. So this allows Cosmos-db to keep track of which items actually apply to which documents in our index.
And can you just go back to that example, please?
Sure.
So one of the ways that first of all, I think the first time I even did an inverted index was like 2007 working on Lucene. And the way I explained myself what an inverted index concept is, basically go to any book you have and go back all the way to the index pages. And what do they really do, right? You look over there and you're searching for a term, Cosmos DB. And what are they going to say? Oh, page number 3, 4, or 45 has Cosmos DB, right? And that's a really easy reverse lookup. And if you've done your indexing strategy the right way, it's going to reduce the cost, because your RU charge is going to be so much less, because Cosmos DB engine is doing the least amount of work to get you that data. And in this example, right, let's say you basically have any search whatsoever. If you look at the pricing search, it becomes really easy with something like a binary search or something that could be done behind the scenes, because let's say you're looking for something like, in this case, what's the middle value, like 6675 or whatever. A binary search algorithm would just keep dividing it and very quickly get you that, right? So you have an inverted index here that's pretty high performing, and you don't have to go through traversing the entire data, and that helps you quite a bit. But one thing to keep in mind when you're doing practical projects on Cosmos DB happens to be not just indexing strategy, but also the partitioning strategy. Because a lot of times you may not realize that, oh, this actual query might end up fanning out to a lot of different partitions and things like that. And that's a completely separate story. We might bring up partitions here or there, but today we're going to focus completely on indexing, because, partitioning, I think, is a pretty good topic for another few discussions like that.
Yeah, it's great that you bring up partitioning. It's definitely important in Cosmos DB as a distributed database. Your partition key really helps Cosmos DB find the exact physical machine to go look for your data. So partitioning and indexing definitely are both important, kind of similar related concepts. Today, we're going to be focusing on the indexing side, but as Chander mentioned, we're definitely going to pepper in some tips about partitioning as we go through. So let's take a look at our same inverted index that we just described, and let's show what this looks like with a sample query. So this is going to be an index seek. In this example, we want to select everything from products P, where p.name equals Touring 1000 Blue. So in this case, we can use our inverted index. We start at the root node, and we can traverse to the name property. Now at the name property, we see that all three of our documents actually have a name. So we have all three things matching here, right? But then when we want to find where the name equals Turing 1000 blue, we look and we see this only matches now one document, which is document 2. So this is how Cosmos DB can use the index in an index seek to be extremely efficient. We don't need to load all of the data and look inside of the name property and see which ones have name. We actually can go directly to the document that we want, and we can just seek directly to it. So
yeah, and this is amazing, right? Because basically you get this out of the indexes, but you could also be careful about what you're indexing. And I think that we're going to cover that in the read heavy scenarios. But in this case, it's as simple. Since you already had this particular property indexed, now we can always get all the names, right? So if we had price indexed, we could have got that pretty quickly too. And really, at the end of the day, the faster you get it, well, the lower your RUs, and that's lower your cost. And again, right, one of the things that people get confused about is like, well, is it only money or is it also performance? Well, at the end of the day, RUs are request units, and think of that as how much hardware I'm spending to get things done. And the way I've always, described performance in my own head is not usually time taken to do something. Because let's say you dropped a bunch of hardware on something and on that operation and you got it done in, let's say, 1 milliseconds, right? Is that any better than using 1/10 of the hardware on that particular operation and still getting it done in 2 seconds? So the way I explain performance to myself is, if I can make a query in the least amount of hardware resources possible, that means the query is high performing. So in this case, we're going to have the least amount of RUs just because this was indexed. And the benefit of that is that, of course, it's going to reduce your cost in terms of dollars, but also in terms of the hardware that you're using. That's what RU stands for. So you basically get the best of the both worlds, And we're going to discuss more on the pros and cons of everything when we start doing the query, so you can see in real life how many RUs you're spending and how do they change. So you can use some of these techniques to do performance tuning for your applications. Because, for our clients that are doing, billions of hits on certain days for the last 4 or 5 years, one of the best things about Cosmos DB is that you almost guaranteed 10 millisecond read and response times for 1 kilobyte worth of documents, right? And that's pretty incredible. But then how do you also take advantage of indexing and other strategies to take care of the queries that are really important and critical for your business?
yeah, that's a great point. The using the index, more efficient index usage, so the index seek, it is definitely going to reduce your RUs, and it will also increase your performance, right? So you get both; they go together,
Right.
as you were mentioning. Yeah.
And you pay less.
Yes, definitely. So now let's take a look at a query that's using another type of index scan. So let's look at the precise index scan. So remember, we said the precise index scan is based on a binary search. So in this case, we want to select everything from products P, where P dot price is greater than or equal to 500 and P dot price is less than or equal to 1000. So in this case, we once again start at the root and we see all of our documents there. We can navigate to our price node. We still have all three of our documents, and we can use a binary search to start evaluating these filters. So the first filter that we'll evaluate is P.price is greater than or equal to 500. We see 2 documents match that. And then when we evaluate the second part of this filter, P.price is less than or equal to 1000, we can very efficiently find our one document that actually matched this, which is document ID 1. We can load that back and return it to the user. So using this precise index scan, because we have comparisons, it can really easily use a binary search and use our index in the most efficient way without having to actually read the entire set of index values.
Yeah, and to your point, right, one of the best benefits of this inverted index is it really knows where to go. It's not going to go to the name node or any other node. It knows that's where the price is. That's what you're looking for. Number two, if you got some computer science students over here wondering, well, how is it faster? Well, think about this as a divide and conquer strategy, right? If you do a for loop and you've got like 1,000 records, I mean, you're going to go sequential. That's probably not the best way to solve a problem. But in this case, you're going to divide and conquer, saying, all right, anything less than that particular price, oh, I know exactly where to go. And that's so much faster than the regular scenario of going through every single leaf node possible and traversing the entire tree, right?
Yes,
That
definitely.
happens to be much better, I would say order of n in this case, and definitely faster for you. And going back to Justine's point, faster performance, and of course, less RUs, both at the same time, which is exactly what we want.
Yeah, totally. So let's take a look at a couple more of these RU scenarios, and let's take a look at a couple more of these indexing policies. And we'll do that by looking at an example container that I've already loaded with a bunch of sample data. So I'm going to open my product scale container. You can see here I partitioned it by category ID. I'll just briefly show you what the schema looks like for this document before we dive into some queries. So this is a really simple products document. We have a category ID here. We have a category name, a SKU, a product name, description, price, and then we have a couple tags.
By the way, I really like number 6, small concrete shoes.
I know.
So, why don't we just tell them our secret of how do we do this?
Yeah, that's a great point. So for those of you very observant viewers, you'll see the name is small concrete shoes and the description is talking about an automobile. The tags is plaza. So what does all of this mean? We actually used a library called Bogus to create all of this data. So I'll just flip over into VS Code really quickly and I'll show you this data generator. So this is a really simple data generator. We're basically creating our Cosmos client. We're getting our database. So we're using the CosmosWorks database with product scale. This generator is configured to create about 200,000 documents. So that's how many documents we have in this container today. And I'll scroll down to the really interesting bit, which is actually in our product generator class. Here we're using the library called Bogus to generate all of this fake data. So Bogus has a lot of great APIs to give us all sorts of stuff, including like a product name from commerce and a product description. So if you're looking at the data and you're thinking, where did they get those crazy names? No, we didn't make them up. We used this really awesome library to generate them for us automatically.
This is cool. I mean, I really like this library. You can get a lot of data going pretty quickly, and you can start testing without having to worry about, oh, are we using the wrong data? Especially my Fortune 500 clients, one of the biggest issues is, what data are we going to even test on in the beginning? And a lot of POCs, I mean, this is so cool.
Yeah. And I also want to mention, because it's going to be important later for our queries, what the categories are. So we didn't generate random categories. We actually wanted to stick to a set of 16 distinct categories here. And the categories for this example have the format of like kind of category group, comma, category. So here we have components, comma, headsets, and a bunch of other categories here. This is actually a really great chance to call out a new feature for Cosmos DB that we're not using, but would greatly improve this partitioning strategy. So there's a feature called hierarchical partition keys. So say instead of storing these categories together as sort of a concatenated string, if we wanted to create a hierarchy where the first component of our hierarchy is this first bit here, components, and then the second property in our hierarchy would be this subcategory, which would be headsets in this case, or pedals, saddles, what have you. So that's a really great opportunity to use hierarchical partitioning for this category, for this container. Due to the queries that we want to show you today, we decided to keep them all kind of concatenated together.
I just want a clarification because I know we've been using it, but I don't think we're using that in production yet. Is that a final feature now, or is that just part of GA?
Yeah, so it's actually a feature that's in public preview, and you can use it through the .NET SDK with certain, I think it's 3.27.0 preview,
Wow.
and it's also available in Java.
So just so you know, it's only 3,
so
right? You can even use 2, by the way. You can do hierarchical partitioning up to 2 and max 3 levels.
Yeah.
Is that right?
It's actually, yeah, so you can have 2 or 3 levels. I guess if you just had 1 level, that would just be a normal partition key. It wouldn't be a hierarchy, yeah.
Right.
So,
and by the way, I know this is code that we wrote, but is there a way we can share it with our viewers so they don't have to write all this code to generate stuff? And, of course, we didn't do the best job here because we were trying to do it fast, but we're more than welcome to share it, right?
Yeah, totally. So this data generator is actually available in my public repository here. So if you go to jcocchi/dataload products, you can see we've created a simple README to help you get started and all of the sample code to generate this data set if you want to try this at home after the presentation.
Perfect.
So let's flip back into our data explorer here, and let's start writing some queries so we can actually show you all of the different scan types. So the first,
Can you make it a little bigger? You know, the older I get, I don't even know what happens to me. I was like, I like it like bigger fonts. Sorry.
sure, yeah. How does that look?
Oh, that's perfect. Yeah.
Okay, great.
Well, by the way,
So,
in the chat, if you're not able to see the font, let us know, and we're more than happy to make it bigger.
yeah, definitely. We want to make sure everybody can see all this great content. Okay, so let's start out with an index seek. Remember I told you that an index seek is an equality or an in filter. So we're going to start out by saying select star from C, and then let's say where C dot category name equals components.
And by the way, what's our partition key here? Just so we're on the same
So
page.
I've partitioned this collection. It's actually partitioned on category ID, not
Mhm.
category name, but we're showing these filters, these queries with the category name, just because it gives us a little bit more flexibility in the range of things that we can query with.
Sounds great.
Yeah. So taking a look at this query, we told you that it's an index seek. So we can scroll down, flip over to the query stats blade. I apologize. It's a really big font, so not a lot of things show on the screen at one time. But here we can scroll and we can see our request charge. We can see this
23
query
RUs.
costs 23 RUs.
Mhm.
And there's plenty more to look at here if we scroll down. What I'm actually going to do, instead of scrolling by each one by one, I'm going to download this per partition query metrics, and I'm going to open this Excel file. So this will allow you to see where all of the time is being taken processing this document. Let me see if I can make this a little bit bigger too. Let's just go to, oops, sorry, Control Plus doesn't seem to be working on this, but
at the bottom right, you see where 100% is. You can actually move that slider. Sometimes
yeah.
Oh, perfect.
Great, thank you. I forgot about that. I forgot where that was for a second. So you can see here that we actually have two physical partitions in this container. We have partition 0 and partition 1. And
By the way, for those wondering that how did you create two partitions, I think there's a cool technique you can use, which is basically start with 20,000 RUs, right, when you provision it, and you can always bring it down, but now you have two partitions. Is that right, Justine? Is that how you did it?
Yeah, exactly. So in order to force my container to have two physical partitions, what I did is I created a container using autoscale, and I set it to 20,000 RUs. So because Cosmos-db can serve 10,000 RUs from one physical partition, as soon as you ask for 20,000 RUs, it knows it needs two physical partitions to serve this request. So that's a cute little trick you can use to force Cosmos-db to create a certain amount of physical partitions. And then, of course, you can feel free to scale back down later. You can scale back down to 10x the highest value provision. So if I create with 20,000, I can scale down to 2,000 RUs. I've actually changed my container to now have 4,000 RUs for this particular container. Yeah, so let's take a look at the metrics that were actually output here. So we can see this matched about 200 documents, and we can see the size of these documents that was returned. We see our output document count. So all of the documents that we retrieved were actually also in our results. We can look at the output document size. These match because we had the exact same data that was actually returned. And this is
where I add a little bit here, right? Because a lot of times your output document count is basically going to be the same as the retrieved document count. But let's just say you do a count. In that case, you won't really retrieve those documents, right? Like you won't really output them, but you will still see them if you do a count one or some kind of
right. Yeah, there's several reasons that your output document count might be smaller if you're doing aggregations. If you have a projection, you might see your output document size be a lot smaller if you reduce the number of properties that you're actually returning back. So there's different ways to tweak these values and get smaller results than were in the initial retrieved set. Yeah, so our index document hit count. So we hit 200 documents from our index. And here is an interesting bit that you can use to really help tune your queries and understand where time is being spent. So we can look at our index lookup time. We see that it was about 0.24 milliseconds. Our document load time was the bulk of the time for this particular query. We see our query engine execution time, and we weren't using any system functions or user-defined functions. And we also have some time for our document write time. So these query exact metrics per partition right from the portal will really help you debug your queries and will help you understand what's going on behind the scenes.
Just wanted to talk about this part a little bit. I don't know if they paid attention, but don't worry about opening it again. But the fact that it's on 2 partitions, you were able to see that one of the partitions, the query time, really the index time was 0.05 milliseconds. That's barely any, because really all the data was in one of those partitions, because these are, when we think about it, right, we have physical partitions and we have logical partitions. And since we don't have a lot of data, right, I mean, a physical partition can now, I think, get up to 50 gigs, used to be 20, is that right? And basically, the logical partitions can be tons. But let's just say those 200 records were in one of those logical partitions, which is just part of one partition, and bulk of that query, the time is going to be on that partition only. And to your point, I like the fact that you even thought of creating multiple partitions. One of the things that we noticed, 9 out of 10 clients test a lot of Cosmos DB without partitioning at all. A lot of times, right? They usually do it on one RU, like 400 RUs to start with. It's a good POC. And by the time they get in production, they realize, oh my God, we're getting a lot of data, right? We got to do a lot of partitioning. So one of the things I highly recommend is anytime you do something, at least have 3 or 5 partitions at least. So your POCs, you kind of know how things are working and how things are going, because you'll uncover a lot of things way ahead of time, then getting to production, and then they call us saying, hey, we really need you guys to come in because we didn't anticipate this. So I really like the fact that you started with 20,000 RUs and then got it down to 4,000 because cost is low, but you were able to get 2 partitions. You could have done 3 or 4, whatever, right? Even with 2,000 RUs. That's a very good hack, which it's very, very helpful, definitely. So thanks for that.
Yeah, it's actually important to call out. That's a great point. So if you know that your application is going to take a lot of physical partitions, it's definitely important to test with more than just one. But if your application is small and you don't expect to grow beyond 1 physical partition, it's definitely okay to use that too, right? So Cosmos DB is built for any scale, very small and very large. So it really depends on your application. I wanted to show with 2 partitions just to make these queries a little bit more interesting and show you really the multiple dimensions that can be represented in those query metrics. Cool. So let's move on to the precise index scan. So remember I told you that the precise index scan is using a binary search. So we've already showed an example in the slides that searches on price, which is a very high cardinality field, right? But now let's actually show a different example. Let's use the starts with function. So let's say select star from C where starts with, and we're still going to be looking at our category name property. Of course, I can't type. And we're going to say where our category name starts with components. And I'm going to pass one more parameter here. I'm going to say false. Now, false is the default for this function, but what false does is basically tells it that we want a case-sensitive search. So case-sensitive searches are able to use that binary search, and it's able to create that precise index scan. So if we scroll down here, and we can see the request charge is 21 RUs. Now, you might remember the RUs for the index seek was actually 23. This is 21. This is because the cardinality of the property really plays into effect here, since there's only 16 possible values, and actually starts with components, covers a large chunk of them, as we showed you what those categories were earlier. This is not adding very much to our index charge, and that's why you see the request charge is a little bit lower. So it's really important to know what type of scan that you're using and the efficiency of each of these scans, but the exact RU numbers could vary depending on many factors: cardinality, size of documents, and all of that goodness. So this is
actually, sorry, go ahead.
Yeah, I was just mentioning that this is the precise index scan.
Yeah, and just to add to that, that's a great point, because you got to think of all these different, factors, including cardinality. So one of the things you got to keep in mind is that actually this query would have been slower. It would have taken more RUs if you had the exact same data coming back, right? The cardinality was slow because the previous one was literally a point query because you're looking for that particular data and that's what it is, right? So equality queries will always be better. Here you have starts with, it'll be probably 1 or 2 RUs slower. Is that a right assumption? If everything, given everything else is the same, this would be a little slower than the previous one. What do you think, Justine?
Yeah, I definitely think it would be slower. So we can scroll down and look at all of these times. I don't remember exactly what all the times were, but yes, so we would spend likely more time on the query engine execution and definitely more time on the index lookup.
By the way, can we actually show them the settings on how we index this, or we just left it default? That's fine, you know?
Yeah, so this container is using the default indexing policy. I can flip and show it really quickly, and then I definitely want to get through all of the other index types that we have today to show. So this is just the default indexing policy for Cosmos DB. I didn't do anything special to change the indexing policy.
Perfect.
Cool. So moving on to our expanded index scan, I'm actually going to change from a case insensitive scan. I'm going to change this to true. So this will make it case sensitive. So if we run this query, we can see that our RUs went up very slightly. They're still 21,
Wow.
but instead of 21.16, they're 21.759. So this is that expanded index scan. So as we mentioned, this is slightly less efficient than the precise index scan, but it's still very efficient and will still give you relatively low RUs.
You know, it's amazing because a lot of times you see data and you're dealing with data that's written by a different team or whatever, and a lot of times that data may not be in the way you want to query. So this is almost like, oh, you know, I could actually, I don't have to worry about case sensitivity at all by just saying true. And really, I didn't even pay a single extra RU. I mean, it's less than what? Definitely less than 1 because it was 21.16 or something.
Yeah, so the exact RUs and the difference will definitely depend on your data, the cardinality. There's many factors that go into this, but for this data set that we generated, yeah, the RUs is relatively even. So let's take a look at our next index type, which is the full index scan. So here I'm going to go into ends with, and we're still going to be looking at the category name, but instead of looking at components, let's actually look at petals. And I'll get rid of this. We'll just use the defaults for this query. So this is actually going to be an expanded, a full index scan. And if we look at our query stats here, we'll see it costs more RUs, right? So 26.47. And if we look at the index lookup time, we can see the index lookup time is roughly double what it used to be. So we're actually needing to look at all of those values in our index, and that's why our RUs are more, and it took a little bit longer to execute. Cool. So the last index type is the full scan. But before I show you the full scan, I'm going to go back and show you just one more index seek. So let's, instead of saying select star from C, let's instead add an aggregation here. So we'll use count of 1. We can say select count of 1 from C, where C dot, oops, messing up my caps lock, category name equals.
You know, I'm so glad you're doing the typing.
I know. I feel like I always forget how to type as soon as I go live, right?
Me too.
Okay, so if we
Everyone.
execute this, we can see there's 12,000 documents in here that have this category name component petals. And if we look at the query stats, this was actually very cheap. This is because we didn't actually need to load any documents at all. We were only able to look at our inverted index. We can find exactly which category has the name component petals. We see exactly how many, and we return the results. So this is an extremely efficient index seek. And if we wanted to change this to a full index scan, so remember I mentioned there's some aggregations and system functions that you can group to kind of create this full index scan. So I'm going to go ahead and change this. Instead of where c.category name equals something, I'm gonna change this to,
Justine, can we just leave this query as it is and type the other one in the next line so they can see the difference, if you don't mind? Sorry, adding a lot of work to you on a live show.
sure, let me go ahead and type this and then I will paste the other one back. Okay, so C dot category name and component. So this time, instead of just looking directly for one component, we're going to try to find all of the categories that contain this component. So I'm going to go ahead and execute this. And we can see that there's 62,000 documents that contain the component's category name.
Wow.
But if we look at the RUs, we see this cost us 2,700 RUs. So this is a massive amount of RUs, right? This is because we are not able to use the index at all. We actually had to load all of these documents and do the processing from the documents themselves. So this is the case that you really want to avoid. And if you do have any queries that are using a full scan, it's important to try to see if you can rewrite them and use the index. Cool. So
great point. I mean, because we definitely want to make sure that your partitioning as well as indexing strategy is such that you are thinking of your queries first. One of the things that I've always encouraged my clients to do is, why don't you just write down in business sense what your queries are, and then accordingly design your strategy. That includes your partitioning as well as indexing strategy. And by the way, you're just doing count stars here, by the way. That is, if you're coming from the SQL background, that's a count star. And 2760 RE is quite a lot. Now, I think our data set is about 200,000 records. Is that correct?
Right. So this is depending on the size of your data. So that's why the cost is so expensive. Of course, these two queries don't do the exact same thing. So I'm not suggesting that you just rewrite it to use an equality filter, but it's important to think about what type of index usage you're using and try to make the most performant queries that you can if possible.
Yeah, because the index seek was somewhere around 20, 25 or less, I would say, RUs versus this. And they're definitely different. But let's just say your application has a way to know what the category name is and its index. I mean, you definitely want to take advantage of that solution over definitely this one.
Right, totally. Cool. So now that we've shown you examples for all of these index usage types, let's actually hop back over to the slides. And we will continue on covering about read-heavy index patterns.
That's cool. So, pretty much any application you take, we have a lot of read-heavy scenarios, and, Cosmos works great for it. Cosmos also works great for write-heavy scenarios. So one of the benefits of Cosmos is that you have an inverted index, and that can include as many fields as possible. So let's say you have a big giant object with 200 different properties or whatever, and you just decide that, we're going to query mostly 5 of those or even 6 or 7 of those. You could individually go and say, all right, I just want to make sure that my index contains these. So that's your inclusive policy. And if you go with exclusionary policy, which means, by the way, I want to make sure that anything in this particular object is excluded from indexing, because by default, Cosmos would index everything. So in that case, what you can do is everything is excluded until I add something that needs to be included. And you can change that anytime you go. You can do this programmatically. You can do this on the portal whatsoever. It's a very simple way to do this. But it's important to understand that if you exclude an entire object from indexing, what's going to happen? Well, any new properties that get added by, let's say, another developer may not even know that the entire property is not going to be included in indexing, right? So that's the only downside there. But if you have a policy ahead of time and you already have factored that thing in, perfectly fine. Now, the cost of that would be a lot lower. In fact, if you change your indexing policy to just go with the few properties that are read heavy for some reason, right? For example, let's take an example of, actually, let's just look at this particular example where we had, actually the last slide, I think, had that. Oh, the next slide has it. Yeah, so next slide, right? So I don't necessarily think I would ever query for description, but I can easily see myself querying with an ID. If I have the ID, and mostly I query with a name, pretty much. And, look at that, like metadata. Metadata's got skew in it. And, a lot of times what I've noticed is people, what they'll do is they'll take the skew out of metadata and put it as part of a regular property because they want it to be indexed. But the cool news is you don't need to do that. All you got to do is tell Cosmos, hey, I'm going to, include metadata / as skew, and that takes care of it itself. Because, one of the examples I can give you is Best Buy. anytime I have had to call one of their customer service people, they'll tell me, can you just tell me the SKU? Because what they're really doing is they're internally querying the SKU. They're not going to go in there, say 27-inch monitor, LG or whatever, right? They're just going to query the SKU. So in this case, we already know that there's a few things we need to query by. And let's say down the line, if someone comes and says, by the way, I want to do this by the date whenever it was created by. Okay, fine, right? No worries. We can go change the indexing policy so quickly. And next thing we know is in just a few seconds, well, it depends on your data. Well, in a lot of cases, it could be a few seconds, but eventually it's not that much work to get that added. So that's another cool thing to do.
That's an important call out. For collections with a lot of data, it definitely takes a lot longer to update the index. If you think back to when we showed you the inverted index, the tree, what Cosmos-DB is actually doing behind the scenes is building that inverted index. So for collections with a lot of data, it will take a lot longer to build. So sometimes indexing changes can take just a couple seconds, and sometimes they can take much, much longer. But it depends on your data. So
absolutely,
that's
and that's why I think, to your point, right? It's part of the strategy that we are going to do. And whenever we decide what our query and all is, we could already have an indexing strategy. And of course, there are going to be new properties added all the time, and we could do it both of the ways. And if you look at this slide, right, I mean, the included path basically saying we're going to do everything except e-tag. Oh, sorry, that was the previous slide.
Let me flip that.
And that's just, Cosmos making sure the e-tag property that it injects is completely excluded. That's it. And that's just Cosmos handling that for you. But you could have easily said included is, let's just say, the name or SKU or whatever, and excluded is everything else, right? So that's as simple as that, going to the portal, doing it. You can also do it programmatically with your APIs that you use. Let's say .NET SQL API. It takes care of that for you. So that's about it for the read heavy patterns, and highly recommended, because you'll see differences of, if you did an index ad, you might end up spending, let's say, 30 RUs, and the moment you index it, you might be like 8 RUs in certain cases. I'm just giving examples on smaller data, not the data set that Justine had, which is like 100,000 records, right?
Yeah, so that's a great point. So we've covered some, patterns that what you might need to consider for read heavy workloads. But how does this change for write heavy index patterns? So we talked a lot about, indexes, and how if you add everything to your index, your queries can be very flexible and you can query on any property, right? Even those metadata properties. But so should I just always index all of my properties? As we kind of alluded to this, so every insert and update operation actually requires updating that inverted index with the new data that you just added. So even for updates to a document, you could still have to end up re-indexing the entire document. So it's really important to, instead of just blindly including everything, it's typically, or excluding everything, right? It's typically best to strike a happy medium and find something slightly in the middle. So let's take a look at an exercise, and we'll look at optimizing an indexing policy for some common operations. And we're actually going to do this following the lab that is provided with this Learn module. So let me switch back over to the Learn module really quickly. And if you scroll to the bottom here and we go to the exercise, you can see it actually comes with a VM. So if you sign in and you launch this lab, you can actually do this all for free in the VM. Today, I'm just going to do this demonstration on my local machine. So we won't use the VM today, but if you're doing this at home and you want a free way to execute this, feel free to use that VM.
And by the way, you don't need an Azure account, because a lot of people ask that question. It's already there for you. It's on your browser. You don't have to worry about booting up a crazy VM. Earlier, I thought that was going to be the case, but when I tried it, was like way faster, and seems like VM would, the perceived VM, quote unquote, performance.
Yeah, right. Totally. Cool. So when I get the code that's associated with this repo, we'll flip over here and I'll just show you really quickly what this looks like. So kind of a tour of this code. Of course, we have our endpoint and our key. We're creating our Cosmos client here on line 7. We're getting our container. So we're still using the Cosmic Works database, but this time we're using the products container. We're just going to read a simple file and replace with a new ID. And then if we were able to deserialize this item into a object, then we're going to go ahead and upsert that item to the container. So what does this item look like? We provided the sample.json here. And this is the exact same schema that I used for my data generator, but you can see these use static values. So it's not using that bogus library to generate lots of random product names and descriptions. It's actually just using this exact same schema every time. We'll just write the same document into our account. So let's actually start. Let's flip back to our Cosmos DB. And I just want to show you what the indexing looks like for our products container. So you can see here, this is the exact same indexing mode that we had up on that slide. This is the default indexing policy for Cosmos DB. It's using the include strategy. So we've included all paths here. That's what this /* means. Basically means index everything. And by default, the only property that's excluded is this e-tag property. So if I flip back over to code and I actually run this, oops, I need to change into the right directory.
And this lab is, by the way, on GitHub. So whenever you try this, one of the things you'll notice is a lot of other labs out there, and you can just pick the ones you would like to try out, and it's really cool.
Right, exactly. So let's just give this a second. I think my computer is angry that I'm sharing my screen and running code, and here we go. So we can see that we've created our item. We've got our item ID, and we see the RU charge. So it cost us 48 RUs to write this document. That's kind of a lot. So let's think back to what we just learned and look back at this schema. And let's think what could be causing this. So we have this huge tags array, right, with tons and tons of tags here. Say for our application, we're not actually going to be querying on any of these tags. We can actually go ahead and exclude this. And we also have the description, which is quite large, right? So why don't we try a different strategy? Instead of using this include strategy, let's try to actually use the exclude strategy. So I'm just going to cut this block. And I'm going to paste it in our excluded paths section. But of course, we still want to be able to issue queries. If we just saved it right now, we would have absolutely 0 properties indexed. Every single property, every single query would result in that full scan. Remember, we showed you the full scan doesn't use the index, and our queries are really expensive. So let's add a couple properties back here that we do want to go ahead and index. So I'm going to add my path. And let's go ahead and index the name property.
And then just so you know, the reason there's a question and not a star over there, you want to talk about that?
Sure, yeah. So there is a question mark that ends, that indicates a scalar value. So name basically equals something, right? If it was a star, it would go ahead and index everything that was under the name node. Now, name is only a scalar value, so it can only have one value there. But say we added, instead of name, say this was like tags. Tags would need a star because tags is an array, right? So if we want to include everything under the array, then we'd want to change that to a star. So it's a really good call out.
Perfect. Yeah, because you may have multiple addresses, things like that, and
right.
you may have seen question marks in some documentation, and you try, it doesn't work. Well, stars the way out. Now, be careful, because you also need to know you don't want to keep indexing things you don't really need. So that's another thing to keep in mind always. But I like this because in this case, what we're saying is we only care about category name. Is that the only thing we did here, or is there something else we did?
Yeah, so we did name and category name.
Perfect.
Here.
And anything else, we're not going to be doing queries on that. So let's just forget that. And we're only going to include these two. So let's run this and see the audio drop. My guess is we're probably going to be less than 10. We had 28 previously. So let's see what happens.
Yeah, let's see. Okay.
It's 200,000 records, so I could be wrong. Let's just see.
So this is actually against our regular container, our product.
Oh, this is just product.
Yeah, so we're just creating documents right now. So we can see.
The previous one was 48. I'm so sorry. I got so excited. I cut you off. I'm so sorry. 48 to 8.
Yes.
Wow.
So we can see that just by excluding all of those huge properties, we saved ourselves tons of RUs when we're not indexing tags, which we weren't going to query on anyways. So this really saved ourselves a lot of RUs and a lot of headache. But the drawbacks of this exclude method, since we've excluded everything, if we wanted to include something later, we'd have to remember to go update our indexing policy, right? So say I didn't want to do that, but I still wanted to get the bulk of these benefits from excluding certain things. So let's change this up a little bit. Let's go back to the include method. So I'm going to put this back in my include block. But instead of excluding everything, I'm just going to go ahead and I'm actually going to try excluding that tags array itself. So if we exclude tags, and maybe let's also exclude description. I don't think we're going to be querying on description, and the description property is also kind of long. Description is a scalar value, so we get a question mark there. Since we have included star, let's get rid of these. Oops. So hard to work on such a small screen.
Yeah.
Okay.
I'm really not jealous of what you're doing right now.
You're screen sharing next time, right? No, I'm just kidding. Okay, so we're updating our indexing policy. So just to review, so we're still using the include path strategy. We have everything included, but what we're doing is we're excluding some properties that we know are really big and bulky and are really contributing to those RUs. So hopefully when we've excluded these, we can actually see our RUs go down. Maybe not by quite as much as when we excluded everything and just included 2 properties, but hopefully we still see far lower than 48.
That's
okay,
incredible.
so here we see
9.71, not bad at all.
Yeah, and the only thing we did was exclude those 2 huge properties. So it's really important to look at your actual data model and look at what are the properties of your data, what is really big and bulky that you're not querying on. Say I did want to query on tags though, say I wanted to query on like tags name, maybe it's not a good idea to exclude it from the index. So in that case, we just have to eat the rate cost, right? So it's always a trade-off.
By the way, why don't we do this? Why don't we just query on SKU for a second? Just take that SKU and see what that costs us without actually including it.
So right now I have everything included. So yeah, let's do that.
Oh yeah, don't forget that. Don't worry about it.
Let's go back to the exclude path.
All right,
we can actually, without changing this, we can go ahead and query on description, right? So we know all of the descriptions are the same. Let me just grab something here.
Yeah, you can do starts with.
Yeah, let's do that. So we're going to add a new query. Let's say where starts with c.description.
Yeah, and people in the chat, right? If you have a scenario you want us to cover, more than happy to.
Cool. So here I only have 3 documents. They're all exactly the same. So we know that they all matched this description. I can't scroll to make the description show, unfortunately. But we can look at our query stats here. And we see this only costs 2 RUs. So we only have 3 documents, even though this property isn't indexed, because our total document size is so low. This charge is still quite low.
And this would be completely different if we were in the other data set, which is product scale, that had 200,000 records, just so you know.
Right. Yeah. If we queried on description that wasn't indexed on that property, on that container, it would definitely cost a lot more. So let's do one more thing. What if we didn't actually care about indexing at all? This is probably a pretty rare case, but we also want to note that if you want to turn indexing off for your container for whatever reason, you can actually go ahead and set indexing mode to none. So I'm going to go ahead and save this. We'll update our indexing policy. Again, it just takes just a couple of seconds because we only have 3 documents. So updating that inverted index really doesn't take that long. I'll switch back to our application. Let me run this one more time, and we'll see how this RU changes. So here we can see if we turn off indexing entirely, it still costs us about 7 RUs. That's because of this data size. It's quite a big document, so even with no indexing, it's still going to cost some RUs to actually go ahead and upload that to our container.
Cool. And then, real quick, right? So one of the things I've also noticed is when you go to documentation, this is a lot of my clients come to me and tell me, by the way, you guys say that order by, it could be done in a simple query situation, right? And then you start doing, you actually have to have a composite key. So the interesting thing there is that is actually true. They're both true, and your query won't even run if you don't have a composite index. And can we show them an example of a composite index real quick?
Sure. Do you want to help me write the syntax
Yeah,
for
absolutely.
the
We could do that.
index? So let me go ahead and grab our default indexing mode back. Okay, so what would it look like if I wanted to add a composite index to this container?
So one of the things we could do is we could just order by, right? So let's just say select start from C, order by any two properties.
Oh, you want
And
me to
maybe
run
we
it
can
through?
just do ascending. Well, forget ascending or descending for now, but let's just see if we get any results back. Because by default, we won't get anything back because we don't have a policy. And I would like for them to see that particular example.
Cool. I'm just going to wait for this indexing policy to save back. Okay, looks like it's saved. So let me close all of these. I don't remember exactly which tab we were working on. So let's go to items, new query. Okay, so select star from C. We just want to do an order by. And then let's say C dot SKU and name, maybe?
Yeah, pretty much any two properties. So, or name or category name, whichever you like. And I think a comma is better. I think it's going to take a comma there, I guess. Let's try that. So you see what happened? That's not going to work. But let's just remove c.name for now and execute. You can just, partially highlight c.sku and execute.
So I just want to, for the audience, so as we were mentioning, it's not supported to do an order by multiple properties if you don't have that composite index. So let's just show what an order by for one property would look like. And let me reduce that back. Okay, so.
And that worked.
For this example, since all of these documents were created in a static way, they all have the exact same SKU. So they're just returned in any order. But cool, that did work. So how would we add a composite index to this?
Yeah, so what we can do is take both of them and add that to our, going back to the settings, indexing policy, and basically go all the way to the end and add composite indexes. And it has to be the same order, by the way. So one of the things you got to keep in mind is, I forgot the query, but let's just say you have, property number 1 and property number 2, and whatever comes first has to be the first path as well as order. Those are the two properties here. Line number 16, you can say path, and the path would be slash or name or whatever we use there, and order ascending. And I think here you have to say ascending, and in your query you can say ASC and DSC, right? So yeah, here you have to give the entire thing. And then you got another comma, and well, actually this is good enough. So that is good enough for, wait, sorry. So we still have another property. So you got comma and repeat the same exact thing. You could just copy paste the whole thing, I guess. And was that the category name?
Let's do SKU.
SKU, yeah, that's a good one.
Cool. So let's go ahead and save this. Oops. We got an error.
What's the error?
His name value.
Wow, this is so even hard to see.
I know.
But in short, let's not worry about getting this.
Yeah, let's not. Sorry, it's difficult to debug with such a small surface.
Yeah, because we don't want to spend too much time on this, right? Because this is really not the topic for today. But in short, I would just want to let people know that whenever you have more than one property, you're going to have to create a composite index like that over there, and you have to give it the direction. So if, let's say, your order is ascending, then and the second property is also ascending, you're going to have one for both ascending, and you're going to have another composite index for both descending. And if you want another one, you'll have to have ascending or descending, or it got to be in the same exact order. And that order has to be the same exact order in your query. So that's something to keep in mind whenever you're doing this, because this is something that comes up all the time. It's all over Stack Overflow and things. It's just a simple pattern that you can follow.
Yeah, cool. So let's hop back over to our slides now, and we will continue with a knowledge check. So we covered a lot of stuff today. Let's go ahead and check our knowledge, and you can actually test your knowledge in the chat. So we're going to show the first question here, and you can actually vote yourself at aka.ms/polls. And we have a QR code here to make it super easy for you to find if you want to take this question. So the question is, your team has written a SQL query for Azure Cosmos-db SQL API with the following text. Select star from C where c.skew equals RD3387G. So which lookup method is the query engine actually using for the skew filter? Chander, do you want to talk about a couple of the options and see which one we think it might be?
Yeah, absolutely. So full scan, it's interesting because full scan means you're basically going to go through pretty much every single record out there, right? And what we're really trying to do is we already have the skew number. So that's interesting, right? And do you want to talk about the difference between index seek and scan? Of course, seek's always faster, but why?
Yeah, so as we mentioned, an index scan means that you need to scan through multiple values in your index to figure out which one it is. Whereas for index seek, the index knows exactly which value to look at, and it doesn't actually need to scan the entire range. So in this case, since we have an equality filter and we're looking for one specific value, what do we think the answer might be?
You know, if I were to go with this, assuming this is indexed, I mean, of course, looks like an index seek because right there, I have the value and I'm just going to go right there, right? And my index knows how to get there. What do you think?
Yeah, definitely. This is an index seek, and we see votes coming in from our audience. Thank you so much for voting. It looks like mostly everybody got it correct. So
Wow,
that's
amazing.
awesome. Thank you guys for voting. And this is an index seek. The index knows exactly which value to look at.
I bet our audience is going, the question was so easy for us. Well, we know. Thank you. Cool.
Cool. So this is our second question.
Yeah, and I can take this.
Sure, yeah.
Which property? Now, this is theoretical, but definitely gets important as we start designing our indexing strategy. Which property of an indexing policy should you set to disable all indexing for a container?
Yeah, so let's take a look at the examples that are given here. We have A, indexing mode. So we saw before the indexing mode by default is consistent, but you can also set this to multiple values. So that could be an interesting option. In B, we have excluded paths. So I know that the excluded paths allows us to specify which properties are not indexed, right? So we can have the exclude policy on our container where we kind of like exclude everything, and then, or we can exclude certain paths. So that definitely sounds like it's sort of disabling some indexing for a container. I don't know if it's disabling all indexing. And then we also have option C, which is automatic. So the automatic property of the indexing policy, when set to true, what this means is Cosmos DB will actually automatically index all of your properties as they're written. So I'm not sure if that one fits. I don't know, Chander, what do you think? Which one is the right answer?
Yeah, the C one is kind of the odd one out, right?
Yeah.
The indexing mode, well, let's just wait for them to respond before we give our answer, I think.
Yeah, it looks like we have a couple votes in. It's kind of a split decision here, so we don't quite have consensus.
Well, I can see why, because technically you go to excluded paths and you go, wait a minute, exclude everything. However, you could also go to indexing mode and say, well, I don't really need anything. Indexing mode is none, right? So if you're confused for the right reasons, because I'm too, right? But if I were to pick one, I'll probably pick A. I don't know. What do you think, Justine?
Yeah, I think it's A. And A is the correct answer. So
Whoa.
congratulations to those of you that got it. This is definitely a tricky question. So as we saw in our demo, we can actually set indexing mode to none. And when we have indexing mode as none, it will disable all indexing for a container. But you brought up a really interesting kind of nuance, right? So for the excluded paths, if we exclude all paths, we also effectively have no indexing, but the indexing isn't actually disabled for the container.
Right.
It just means that we've excluded our paths, right? So this is a really nuanced answer, but A is the best way to actually disable all indexing as opposed to just excluding the paths that can be indexed.
Yeah, and by the way, I know one of the things that all my clients always ask that I wanted to reference here is that a lot of times what happens is when you change your index down the line, you went from excluded to included, or you added another property or whatever. One of the frustrating piece some people have, especially in production, when you have a lot of data in there, right? Let's say you have millions of rows or whatever, is that it's going to take a while, and you don't sometimes know when it's going to be done. So one of the things you can do, and this is a really cool trick that we use, is every time you have a container response programmatically, it actually has a header. It's a really long one, but you can Google it. So I'm just going to give it to you. It's x-ms-cosmos-db-collection index transformation progress with dashes in between, in case you want to know programmatically when your index actually got done. Because I guarantee most of you are programmers like me. You're not going to go to the portal. You're not going to get it set it up. You want to do it programmatically, and you want to know when it happened, and you're not going to wait for it. Because a lot of times that kind of stuff happens to me at 2 a.m. in the morning, and I'm not in the mood of looking at the browser. So if that works for you, that'd be great. But the good news is that class that I just mentioned, right? It has a lot of other things that you can start looking at, especially when you're using the .NET API. I can't speak for a lot of other APIs, right? But they will still have the headers. Don't get me wrong. But this particular one, take the container response.headers in that particular class in the .NET SQL API.
Yeah, totally. That's a great point. It definitely can take a while to index everything. So knowing when your indexing is complete and when you can utilize those new indexes that you set up is definitely important. Cool. So let's go ahead and summarize everything that we learned today.
Yeah, so I think we talked about customizing an indexing policy for read-heavy workloads. We had a little bit extra stuff than the lab you had up there, but hopefully we shared that code so you can try some of that on your own, and we encourage you to try the lab too. And we also discussed some of the other ways to do indexing policy on write-heavy loads. And hopefully in the future we'll see you for another one on indexing, maybe composite indexing or partitioning and other things.
Yeah, totally. So if you want to learn more and you want to actually follow along with this Learn Live module, you can learn more at this link here. There's also a QR code conveniently for you. And this is the Learn module that we completed today. So customize your indexing policy in Azure Cosmos DB SQL API. We have a link and another QR code for you. So please go ahead, check this out, do the module, learn from yourself, and hopefully you can make better informed decisions about your indexing policy in the future. We also want to call out that this is part of a series. So there will be another Learn Live next week on June 22nd. It will be talking about measuring index performance in Azure Cosmos DB. So for those of you that are wondering how all of this affects your performance, be sure to check out this module. It'll be really great, and there'll be even more great content to help you learn about indexing. And don't forget, lastly, to get certified. So here is, again, we're showing our Azure Cosmos DB certification. This is a really great certification to really demonstrate all of your knowledge about Cosmos DB and really see if you can design and implement an efficient database and solution.
Yeah, and if any of what we discussed came in your certification exam, do let us know on LinkedIn. We're always there.
Yeah, definitely. All right. Well, that's all the content that we have today. Thank you guys so much for joining us. And thank you, Chander. It was great chatting with you and covering all this great information about indexing policies.
It was fun. Thank you for having me.
Cool. All right.
Bye,
Thanks.
everyone.
Bye, everyone.